Have you ever wondered how scientists uncover materials that could revolutionize technology, like superconductors that conduct electricity with zero resistance or ultra-efficient batteries? It's not just about trial and error. Today, we're exploring how AI is transforming materials science by mapping hidden connections in decades of research. Let's dive into a breakthrough approach that uses matrix factorization to predict new material properties and accelerate discoveries. Imagine a social network where links between people are based on shared interests. If Alice knows Bob and Bob knows Charlie, it's likely Alice and Charlie might share a connection too. Now apply this logic to scientific papers. Researchers have studied thousands of materials, but many relationships, like how a specific material behaves under certain conditions, are missing. Our goal? To find those gaps. The focus of this study: Transition Metal Dichalcogenides, TMD, a class of materials with extraordinary properties. Think ultra-thin semiconductors, superconductors, or catalysts. But here's the problem. Scientific literature is vast, messy, and full of missing data. How do you spot patterns when the data is incomplete? The solution: a powerful AI framework combining matrix factorization techniques. Let's break it down. First, they used hierarchical non-negative matrix factorization, HNMFk. Picture this: you're organizing a library by subject, then subtopics, then specific ideas. HNMFk does the same for scientific papers, grouping them into a three-level hierarchy. The top level might be broad themes like superconductivity, while lower levels dive into specific materials or properties. But here's the twist: they didn't stop there. They paired HNMFk with boolean matrix factorization, BNMFk, and logistic matrix factorization, LMF. Think of BNMFk as a filter that turns messy data into clear yes-no connections, while LMF adds probabilities, like guessing how likely a link is based on existing patterns. Together, they create a three-level topic tree that maps materials to their scientific themes. The results? Remarkable. When they removed papers about superconductivity from the dataset, the model still predicted which materials belong to superconducting TMD clusters. It's like finding a needle in a haystack by recognizing the haystack's shape. This method doesn't just fill gaps, it generates new hypotheses for scientists to test, like exploring how a material used in batteries might also have superconducting potential. And the best part? They made it interactive. Through a tool called Streamlit, researchers can visualize these connections in real time, tweaking parameters and uncovering insights that might take years to find manually. Let's get technical. The team converted thousands of scientific papers into a TF-IDF matrix, a digital fingerprint highlighting the most important words and phrases. Then they applied HNMFk to uncover hidden patterns, grouping similar topics into a hierarchy. For example, the top level might be superconductivity, while the second level could include materials like MoS2 or NBC2, and the third level might specify properties like electron mobility or band gap. But how did they validate this? They tested their model by hiding known superconducting links and seeing if it could find them again. The results? Nearly perfect. Materials like MoS2 and NBC2 topped the rankings, while non-superconductors like Fe2 scored much lower. This isn't just about finding what's already known, it's about predicting the unknown. By analyzing patterns in existing data, the model suggests new materials to test, saving time, money, and resources. This approach isn't just academic. It's accelerating discoveries that could revolutionize renewable energy, quantum computing, and more. Imagine a future where AI helps us design room-temperature superconductors or ultra-efficient solar cells. No lab experiments required. So what's next? Recent advances, like Boolean matrix factorization and message-passing algorithms, are tackling noisy data by refining predictions. Even large language models are being tested for their ability to analyze chemical and material science datasets. These methods are quiet but powerful forces shaping the future of science. Thanks for watching. If you're curious about how AI is reshaping science, hit subscribe. And let me know in the comments, what material discovery would you love to see next? Remember, the next breakthrough might be hiding in a dataset, waiting for the right algorithm to find it. Stay curious, and let's keep exploring the unknown together.